Okay, moving onward into chapter 28, we'll be talking about sources of magnetic field. It turns out that if we have a moving charge, not only will it experience a force inside of a magnetic field, but it will also produce a magnetic field of its own. This also means current-carrying wires, moving charges, are also going to produce magnetic fields, and so we'll go ahead and we'll calculate some of these magnetic fields. There's also going to be interactions between two current-carrying wires. We'll talk about the type of force that we see. And the most important part here is going to be introduction of Ampere's law. So much as I hinted, if we have a charge that is moving, it's going to generate a magnetic field. We can kind of take a look at a moving positive charge right here. And I'm saying it's got some velocity in that direction. It's going to generate a magnetic field. What direction is the magnetic field going to be? What we do is we use the right hand rule again. We take our thumb and we point it in the direction of the velocity vector, and we look at the direction that our fingers are going to curl around this guy. We can kind of see that right up at the very tippy top, the fingers are going to be curling out of the plane right here. Over here, they're going to be pointed downwards into this plane right here. And so the magnetic field, it turns out, is going to be circular around the direction of motion. So if we take a look, remember, if I have a little X or an X with a circle around it, that means that the charge is going to be moving into the page. Take our thumb, we point it into the page right here in the direction of motion for the charge. It's a positive charge. And the current is going to, or the magnetic field is going to curl around kind of clockwise around the circle here. If this is a negative charge, you essentially have to reverse the direction and say it would be in the opposite direction. Now, the velocity of the charge is going to matter, and at the end of the day, we're going to be able to write what the magnetic field is. It's going to be equal to some proportionality constant, mu naught, divided by 4 pi, multiplied by the charge, the cross product of the velocity and the r hat vector, and divide that guy by the radius squared. So first, for this r hat vector, that's going to be a unit vector that is along the radius here. So kind of like I hat is one unit vector along the x direction. The r hat is going to be a unit vector pointing radially to wherever we're looking at. This mu naught right here, that's going to be just a constant, a proportionality constant, and that's going to be equal to 4 pi times 10 to the negative 7th with a unit of Tesla meter per amp. And we will come across this mu naught again, so it is kind of important. In chapter 23, we're going to see that it's related to the speed of light along with the permeability of free space. So the speed of light squared is going to be equal to this proportionality constant for magnetic fields multiplied by the permeability of free space. So we are going to see it again. So let's just take a quick example. If we have two protons that are moving in opposite directions, we have an upper one and a lower one, let's consider the magnetic field that is generated by this lower guy right here. To figure out what it's going to be, it's going to have some constants up front. mu naught divided by 4 pi. Pull the charge on out there. Now let's just take a look at this radius crossed with the r hat right there. Here the r hat is going to point just in the j direction. If you go ahead and you cross the j into r, you can see that it's going to be in the k hat direction. So that gives us the direction of this guy. Now we say that the force is going to be equal to the charge velocity crossed with the magnetic field, so that's going to be the force experienced by this uppermost guy. If we cross this velocity into the magnetic field, we're going to have our thumb pointing in the upwards direction, so the force experienced by the top charge due to the bottom charge is going to be upwards, and also there's going to be some electric force of repulsion away from this guy. Really, the takeaway from this guy is just get really familiar with using the right hand rule and figuring out the directions of magnetic fields. Now we can take this a step further and say, well, if we have moving charges, that's just going to be current. And so we can look at a current carrying wire and say it has some tiny little length dl, it's got some tiny little charge to it, the charge is flowing. Same type of thing is we can say, let's take a look at the direction that the charge is moving, point our finger along that guy, curl it around right there, get tiny little amounts of electric field due to each tiny little dl, and say we can come up with a formula called the Biot-Savart law, which relates this tiny little amount of magnetic field to the permeability of free space that we're already familiar with now, multiplied by the current, and this little dl is going to be in the same direction as the current. This is the unit vector. Again, that's just going to have a magnitude of 1 and point in the radial direction between our little chunk of dl and then the point P that we're interested in, and then the radius squared. If we look at a current that was directed into the page, it's going to have a magnetic field set up around it that's going to be clockwise, and it's going to look pretty much identical to what we've already talked about for the moving charge law, but very important law to keep in the back of your head. So let's just take a quick look of applying this law. Example 28.2. What we're asked to do is we have a current carrying wire. We tells us what the current is and what the direction it is. It's in the negative x direction. We're looking at a little 1 centimeter chunk of wire, and we're asked what the magnetic field is at point 1 and point 2 here. So let's just take a look at point 1 and leave point 2 for you to do on your own. We know that mu naught is going to be 4 pi times 10 to the minus 7th, so we're going to have 10 to the negative 7th divided by 4 pi multiplied by 4 pi. We know what the current is, that's 125 amps. Now this little dl right there, that's just going to be 0.01 meters, and then the direction of it is in the negative x direction, so it's going to be in the negative I hat direction. We're going to cross that with a unit vector that's going to point from our source, the 1 centimeter chunk, up to point P. That's in the positive j hat direction. And we're going to divide that guy by that distance right there. That's going to be 1.2 meters. Make sure I square that guy right here. Now if I cross negative I hat with j hat, what I'm going to get is I'm going to get negative k hat. So my direction is going to be in the negative k hat direction. It's going to be into the page, and you can do that also with the right hand rule. And so you're going to type all this stuff in, you're going to come out with 8.7 times 10 to the negative 8th. It's going to have a unit of Tesla, and the direction would be in the negative k hat direction. And you can do the same for point 2. So let's take a look at applying this for a wire that's running up the page. It's running up the page from negative A to A. We got some current flowing through it. We're asked to solve for the magnetic field at point P right here, away from some wire. So we say that point P is some distance x away, and what we're going to do is we're going to take our wire and we're going to divide it up into tiny little chunks of dl, each carrying some tiny little current. The direction of dl is in the same direction as the current. So this is also going to be kind of a dy that we're going to, at the end of the day, end up integrating up, so we can see we have something to integrate in the y direction, so our integral will work its way up to be the y direction. Now let's take a look at the direction, which is given by this dl crossed with r. We could write that as dl multiplied by r multiplied by sine of the angle in between those guys, and use the right hand rule to figure out the direction, kind of as shown right here. We point our fingers in the direction of the current, curl our fingers around it, and we see the direction is going to be into the page. So r hat is just going to be a unit vector, so that's just 1, and what we're kind of left with is just a dy, and we could also write that as sine of 90 minus phi, or pi minus phi, for convenience, and that way it looks something more like our triangle right here. So we can boil all this stuff down to be mu naught divided by 4 pi. Now let's take a look at the radius. That's just x squared plus y squared. or the square root of x squared plus y squared. And we take the square of a square root, and we're just left with x squared plus y squared. So mu naught dy, can't forget my current. And then I have my sine of 90 minus phi. Now I can use opposite over hypotenuse to rewrite the sine term, and I'm going to say my magnetic field is going to be the integral of all these little tiny dBs. So go ahead and pull all my constants out. Mu naught's a constant, I is a constant. I'm going to have an x from that sine theta, that's going to be a constant. I'm going to pull that guy out. 4 pi. And I'm going to be integrating up my dy, and this is going to be x squared plus y squared now to the 3/2, and I'm going from negative a to a, and that guy is going to boil down to mu naught I divided by 4 pi, and then 2 times a divided by x square root of x squared plus a squared. Pretty much just looked that up in the table and plugged in the negative a and a to save on, but didn't show all the steps to save on space. At the end of the day, if it's infinitely long, the magnetic field is going to boil down to that, which you'll definitely be using. We could also write this as mu naught I divided by 2 pi r, where r is the radius away from the long current carrying wire. So a very important equation to know and be able to use. So let's take a quick look at example 28.4. In this case right here, we have two very long wires that are running into the page. And so what we can do is we can write what we derived on the last page, that the magnetic field around each wire is going to be mu naught I divided by 2 pi r. So that's going to be the magnitude of the electric field. This wire is running up out of the page. This wire is running down into the page. So for each wire, we point our thumb respectively in this direction, curl our fingers around, and we can see the direction of the magnetic field for each wire. This one's going to be clockwise, this one's going to be counterclockwise. And we can see that they're going to kind of add together in the middle. They're going in the same direction right there. The lines get, the spacing becomes shorter. That tells you the magnetic field is larger. And then the magnetic field is going to die off like 1 over r, essentially, give or take. So what we can do is we can say, if we know what these distances are, we can calculate b1 and b2 from using this equation right there, and mathematically sum up the total magnetic field. I'll leave that as an exercise for you to play around with. So let's go ahead and do another application of this. If you remember when we had two protons several slides ago, there was a force of attraction between them. If you have two long current carrying wires, there was a force of repulsion between the protons. If you have two long current carrying wires, think about it, this one's going to be generating a magnetic field, and this one's going to be generating a magnetic field. So this wire right here is going to interact with the first wire's magnetic field, and there's going to be a force involved. If you remember that force is equal to the current multiplied by the length crossed with the magnetic field, and we also know that B is equal to mu naught I divided by 2 pi r for infinitely long wires. Then you can see that this is going to be the current multiplied by the length multiplied by mu naught I divided by 2 pi r. One thing you have to be careful with here is we have two I's running around here, and these currents may very well be different, so let's go ahead and put a prime on this guy. Really what we're talking about is we're talking about a force that's going to be the interaction of this top current, this primed current, with the magnetic field from the other wire, which is dependent on that wire's current. So we can also write a force per unit length as being this equation right here. one thing to be careful of is all the directions. You can kind of conceptually see all the right-hand rules down there. I'm not going to go through that yet another time, but in general, these wires are going to attract each other as if the currents is in the same direction, and they're going to repel if the currents are in opposite directions. Just a quick example, 28.5, we have two wires and they're separated by some distance. We're asked for the force per unit length, so we can go ahead and write that as from the last page. And we're told that the current is 15,000 amps. That's a huge amount of current. So we can write the force per unit length as you kind of see right here. And then I've kind of filled in mu naught and then the two currents. Distance of separation is going to be 4.5 times 10 to the minus 3. We go ahead and we calculate that guy out, and it's about 10 to the 4th newtons per meter of length, and that's actually a really huge number. So when we're talking about large currents like that and small distance of separation, the force can actually be quite large. We can also use the Biot-Savart law to take a look at a loop. The integration all is identical to what I did with the electric field loops. I'm not going to scar you by showing that to you. If you're really interested, check out page 933 in the text. We get the direction to be only along the x-axis using the right-hand rule, and then the result is given by this equation right here. Now let's just take a look at what happens if x is equal to 0. We can write that the magnetic field is going to be equal to this expression right here, where n is going to be the number of loops. Just kind of conceptually think about going around at once, wrapping the wire around a second time, third time, fourth time, fifth time, and so on and so forth. So we can write the magnetic field in the center as such. You can also say, hey, you know what, if I know what the magnetic field is, I can figure out the direction of the current. This looks a lot like this magnetic moment that I talked about a little while ago, where if I know what the magnetic field is, I point my thumb in the direction of the magnetic field and I curl my fingers around. The direction of my curl is going to be the current, so I can figure out what that is. I could do the same if for this example right here. And if you think about it, the maximum magnetic field is going to occur in the center. That's the same maximum that I showed in the last page. And then as you get further and further and further away from the center, the magnetic field is actually going to kind of die off, like you can see here.